Greetings, students. Mr. Keister back with you here again today. The last two lessons we have been going over Unit 11.2 regarding voltaic cells. Like I said, the last two lessons we've been going over how voltaic cells work, how they're set up, and how they operate, and what they can do for us. We're going to talk more about that in the coming next several lessons. I still have the diagram of the voltaic cell on the board. Please make sure that you understand how that works, how it's set up. I took quite a bit of time and detail in going over that. It's very important. They're very important to general uses today in regards to voltaic cells, most notably in batteries. I mean, again, think about it. If we didn't have batteries today, think of all the devices we utilize today that use batteries as their source of electrical power. All that electrical power comes from the power of a redox reaction. So just keep that in mind as we work our way through the rest of this unit. Today's lesson and tomorrow's, we're going to talk about some additional voltaic cell calculations involved with voltaic cells. And so this first lesson today will begin that, and then the next lesson, hopefully, we will finish that up. And at that point, then be done with Unit 11.2. So let me pull the do nows. As you can see, these would have been the original do nows had we been in school, like I've been posting. If we're in Chem 2, this lesson would have been on the 10th of April. I believe in Honors Chem, it's about a week later than that. But again, don't refer to this do nows. Remember that what we are now referring to in regards to not only the daily do nows, but our calendar. I have combined those on one document, which is now available and has been available to you on my Canvas homepage. So make sure you're referring to that in regards to when lessons are actually supposed to be looked at by yourselves, and of course then the related work that goes with those lessons. So let me clear that screen there and pull up our notes for today. There we go. Okay. So again, we're going to start today with additional voltaic cell calculations. Today's lesson and tomorrow's will end up covering this section of the notes. So first thing I want to mention is this. Because cell potential measures electric potential energy per electric charge, a standard reduction potential then is an intensive property, right? It's an intensive property. Remember, intensive properties are independent of quantity, all right? Which means then that it does not matter what amounts the reactants and products are in. It's very similar to density, all right? So if you remember density, I'll do a little graph over here. Remember, density was a ratio of mass to volume. And for a particular substance, whatever its mass was, that ratio of mass to volume is constant, all right? And so you get a straight line graph with a positive slope. And the value of that positive slope, in this case, is the ratio of mass to volume, which is density, all right? Voltage or cell potential is a very, very similar thing. I could draw the same graph whereby this then would be the electric potential energy on the on the y-axis, and charge. This would be measured in joules, as all energies are. Charge, Q, is actually measured in coulombs, right? That's the standard unit of electrical charge, the coulomb. But anyway, since this is a ratio, all right, of potential energy to charge, we have the same situation here that we have with density. You get a straight line, positive slope, and the value of that slope is the ratio of potential energy in joules to charge in coulombs, which is voltage or cell potential. All right. And so here again, regardless of quantity, the value of that voltage or cell potential is going to remain constant. So the bottom line is changing the stoichiometry coefficients does not, in balancing a redox half reaction, does not affect the value of the standard reduction potential. It does not affect it whatsoever. So here we have a reduction half reaction, comes straight off the chart. Our reduction potential chart, remember we're working with this chart now quite regularly. If we look up the value of the reduction of the zinc plus 2 ion to zinc solid by gaining 2 electrons, the value for E is minus 0.76 volts. Again, that negative sign should tell you something. Metals don't want to be reduced, all right? They want to be oxidized. They want to lose electrons because of their electron structure. And so it's minus 0.76 volts. But let's say in balancing a redox reaction that it would require that this half reaction would have to be multiplied by 2, certainly a possibility. And so in doing so, multiplying this by 2, this becomes a 2 zinc plus 2. The electrons now would become 4, and the zinc metal would become 2 as well. Notice the value of E for this reaction is exactly the same as it was before. So even though we took this reaction here and multiplied it by 2 to give us this reaction here, that these two values are still the same. Again, that is because cell potential or voltage is an intensive property, just like density is. Okay? All right, so let's go on to the next page. And keeping that in mind, we will do some additional voltaic cell calculations, just like the ones we did the other day, and take into account this fact right here. So let me erase this, and we'll go on to this next problem. So example 5 says, using the table of standard reduction potentials, calculate the standard EMF for the following reaction. All right, so trying to calculate E cell here using this reaction here. Well, again, this is a net ionic equation, so we need to kind of take a quick look at it and see what's being oxidized here, what's being reduced. So as I look across here, most of these are fairly obvious. Hydrogen, of course, is +1 there. I is -1 there. Chromium is +3 there. I2 is a neutral element, so of course that's 0. In water, hydrogen, of course, with non-metals is +1, 2 of those. And O, of course, in virtually all compounds or ions other than peroxide is -2. So now let's look at the dichromate ion, the first one. I kind of skipped by that one. So again, O here is -2, but there are 7 of them, all right, for a total of -14 on the negative. There are 2 chromiums, but keep in mind the dichromate ion is not neutral. It has an overall charge of -2. So whatever the oxidation number of chromium is, and keeping in mind there are 2 of them, when you figure that out and add it to the O's, we're going to end up with -2, not 0. So -14, and then let's get rid of the 2 there, so that would be -12. So the chromium would have to be +12, but there are 2 of them, so that would be +6 times 2. So +6 times 2 is +12. -2 times 7 is -14. +12 and -14 is -2. So now we have all our oxidation numbers, and as we take a look at that, and we see that chromium gets reduced from +6 to +3. And let's see, what gets oxidized? Well, it's not oxygen, that's -2 all the way through. It's not hydrogen, it's +1 all the way through. But as you can see here, iodine goes from -1 to 0. That's getting more positive, so iodine is being oxidized. So when looking up our half reactions at the cathode and the anode, remember cathode is our reduction half reaction and the anode is our oxidation reaction. So let's look up our reduction reaction first. It involves chromium, and in fact it involves the dichromate ion and the chromium plus 3 ion. And if you look up on your chart here, and let's see, go down about 2/3 of the way down, you will find the reduction half reaction that involves the dichromate ion and the chromium plus 3 ion. So I'm going to write that up here now. I'm going to pull it right off of the chart. So it's Cr2O7 negative 2Aq plus 14 hydrogen Aq, 14 hydrogen ion that is, plus 6 electrons yields 2Cr plus 3Aq and 7 H2O liquid. Again, you can see that our dichromate ion is already balanced, and as is our 2Cr plus 3 ions. So that's good there. If I look up the value of the voltage from that half reaction, it is 1.33 volts. Now, our oxidation half reaction involves I-1 going to I2 solid. Keep in mind when looking up an oxidation half reaction on a reduction chart that it's not going to look like that. It's going to actually be in reverse. So I want to find the I should say I want to find the reduction half reaction that involves iodine going to I minus, but then we're going to flip it around to show it as an oxidation half reaction. And if we look up on the chart, it's right up here on the right side, fairly close to the top. You'll see I2 solid plus 2 electrons yields 2 I minus. That's the reduction half reaction. For us, we're using that as an oxidation half reaction. So we're going to flip it around. And so that would then, taking that half reaction off the chart and flipping it around, would give us 2I minus negative 1 Aq going to I2 solid plus 2 electrons. And remember, when we flip the reaction around to use it as an oxidation half reaction, based on the way we calculate E cell using the minus method rather than the plus method, we do not, I repeat, do not have to change the sign on the value of E. And so based on that reaction, that value of E is 0.536 volts. Now, next, notice here that 6 electrons here are gained in our reduction half reaction, which means 6 electrons have to be released in our oxidation half reaction. So what we're going to have to do is multiply this anode half reaction, our oxidation half reaction, by 3. Okay? So this then becomes 6, this becomes 3, and our electrons become 6. Notice now that our I minus is a 6, as it is right here in our overall net ionic equation, and our I2 now has a 3 in front of it, as it also does up here in our net ionic equation. So that brings everything into balance as far as our entire equation. Now, the thing that we just talked about, the fact that E, or voltage, is an intensive property. I'm going to make a little note here. Multiplying by 3, all right, to balance the electron transfer, all right, does not, repeat, does not change the E value. So even though I multiplied this half reaction by 3, that is not necessary to multiply the value of E, the voltage value, by 3 as well. Because again, voltage is a ratio, right, of energy to charge. The ratio is not changing. If the energy goes up, the charge goes up right along with it to the same degree. So we are now ready to calculate E cell. Okay, so E cell then is E reduction cathode minus E reduction anode. Again, using the minus method, we do not have to change the sign on this. It's already, the equation does it for us. And so that then would be 1.33 volts minus 0.536, which gives us a value of 0.794 volts. Again, remember, as I said the other day, you do not have to do any type of rounding and calculating E. Since these values are determined to be precise, we're not going to change the precision level in any of our calculations. So, question, is this, in other words, using these two half reactions, is this an operating Voltaic cell? In other words, will it spontaneously produce electrical energy? And the answer to that is yes, it is, because that value of E cell is positive. Had that been a negative value, the answer to that question would have been no. In other words, if we had put this half reaction at the anode and this half reaction at the cathode and reversed these two numbers and got a negative value for E cell, the voltaic cell would not operate. It would not. Okay? Very important thing to know. All right. Let's look at the next one, number 6. Again, we're calculating the standard EMF, so we're calculating E cell here again for a cell that employs the following overall half reactions. This is a very similar problem to the one we just did, so let's take a look at that. First of all, I want to see what got oxidized and what got reduced in this reaction. This was pretty easy to look at. It's set up for us pretty much. So here, aluminum solid, of course, is neutral element at 0, as is iodine. Here, aluminum has a +3 charge on the ion. Remember, its oxidation number is the same. Metals hold true. And here, I is -1. So looks like our what got reduced would be iodine from 0 to -1. And what got oxidized then would be aluminum from 0 to +3. So we are going to utilize our half reactions now. Remember, reduction occurs at the cathode, oxidation at the anode. So now our reduction half reaction involves the reduction of I2 to I-, which coincidentally is the same half reaction we used in the previous problem, only there we used it as an oxidation half reaction. Here we're actually going to use it as a reduction half reaction. So when we look that one up on the chart, it is reduction. It's going to look exactly the way it does on the chart as it does here, which is I2 solid plus 2 electrons going to 2I negative AQ. And again, that value, just as it was a minute ago, I hadn't changed, 0.536 volts. Okay? So now, the oxidation of aluminum is our half reaction. So again, when we look up that half reaction on the chart, it's going to appear as a reduction half reaction. So as I look that up on the chart here, it's fairly close to the top. Right there it is. Al plus 3 AQ plus 3 electrons yields Al solid. That's a reduction half reaction. We're going to flip that around, make it oxidation. So that would give us Al solid going to Al plus 3aq plus 3 electrons. All right, plus 3 electrons. And again, we'll pull the value for E for that half reaction. Again, we're not going to change the sign. It's not necessary. That value is minus 1.66 volts. Now, before we continue, I got to keep in mind the number of electrons transferred in a redox reaction must be the same. In other words, the electrons released at an oxidation half reaction and the electrons gained in the reduction half reaction must be equal. And as you can see here, they are not. So we're going to multiply. Here we have a 2 and a 3, so the least common multiple there is 6. So we're going to multiply the top half reaction by 3, the bottom half reaction by 2. So that becomes 3, that becomes 6, and that becomes 6. The bottom one, we have a 2 there, a 2 there, and a 6 there, right? And as you can see then, when we transfer our electrons, which is now at 6, that is equal. So that cancels out exactly as it should. And now we're left with the correct coefficients of our overall net ionic equation up here. So you can see I2 is indeed now 3, I minus is now indeed 6, and the 2 ALs are both 2. So everything has come into balance as it should. Again, based on the fact that E is an intensive property, we do not need to multiply this value by 3. We do not need to multiply that value by 2. They can be left just as they are. So E cell then for this reaction is E reduction cathode minus E reduction anode. So we have 0.536 minus negative 1.66. And that comes out to be 2.196 volts. Okay, 2.196 volts. So again, this is also an operating cell spontaneously. And as you can see, it produces more voltage than the previous reaction, which there again means that this particular set of redox half reactions is going to be able to produce a larger current than the previous one. So again, based on the current requirement for a particular device, let's say that it had to be a minimum of 2.2 volts or whatever. I would not be utilizing these half reactions in that voltaic cell because they're not going to be able to produce enough current to operate that device effectively. It would operate, but at a reduced current. Basically, it'd be like a 60-watt light bulb only operating at about 25 or 30 volts. In other words, the light bulb would work, but it would be dim rather than lit to its full brightness. That's kind of what that a good analogy there is. All right, so hopefully you now see that E cell is an intensive property and that multiplying our half reactions by a coefficient does not change the values of E nor change the value then of E cell. So let me erase this and then we'll go on to our next topic today. Okay, scoot this up. So the next thing, excuse me, a very important thing to know. The more positive the value of E, all right, the greater the driving force for reduction, right? All of these values on the chart are for reduction half reactions. The more positive each of those are, the more that substance in that half reaction wants to be reduced, all right? Note that in any spontaneously operating voltaic cell, the cathode reaction must have a more positive value for E than the anode reaction does. That way, when you subtract the two, you're going to get a value for E cell that's greater than 0, all right, which means it spontaneously operates. In essence, the greater driving force then of the cathode half reaction is used to force the anode reaction to occur in reverse as an oxidation half reaction. In other words, when we set up a voltaic cell, if we want to make sure it operates, we want to know and make sure that the value of E for the reduction half reaction is more positive than the value of E for the oxidation half reaction that we're going to utilize. As long as that's true, then the voltaic cell is going to operate. All right. So let's take a look at our next reaction here, and we'll see how we're doing that. So a voltaic cell is based on the following two half reactions. Here we have the reduction of cadmium from +2 to 0, and here we have the reduction of tin from +2 to 0. Two reduction half reactions. Determine the half reaction that occurs at the cathode and anode. So that's what we're going to do first. All right, well, what we'll do then is let's just look up the values of those two half reactions. Now remember, these are metals, both of these. They don't really want to be oxidized, or I should say they do want to be oxidized, so they definitely don't want to be reduced. Metals don't want to be reduced. They want to lose electrons. And so I'm guessing that both of these are probably negative values. Let's take a look. The cadmium half reaction is right there. It's about, a little over, almost halfway down the left side. And its value is negative 0.403 volts. The tin half reaction is on the right side, almost clear down at the bottom, fourth one from the bottom actually, and that is minus 0.136 volts. All right. So you say, well, they're both negative. All right, they're both negative. How in the world can we set up an operating voltaic cell if both half reactions have a negative value of E? Well, we can. All right. In fact, we most definitely can. Again, remembering what I just said a few minutes ago. As long as the cathode half reaction is more positive than the anode half reaction, we can set up an operating cell. Doesn't matter that they're both negative. All right. What matters is that the reduction half reaction is more positive than the other one. So based on this, our cathode half reaction would have to be the tin one. And our anode reaction would then be the cadmium half reaction, because tin is more positive, all right, than the cadmium one. So here again, even though both have a negative value, all right, even though both of them have a negative value, you can still make an operating cell. And we're going to show that right now. All right. So again, cathode is our reduction half reaction. Anode is our oxidation. We said tin is more positive than cadmium. That's the one we're going to use at our cathode, our reduction half reaction. So this would be Sn plus 2Aq plus 2 electrons yields Sn solid. Its value is negative 0.136 volts. Our cadmium half reaction is going to become our oxidation half reaction. So we're going to flip this thing around to make it oxidation. So this would be Cd solid going to Cd plus 2 Aq plus 2 electrons. Okay? Again, that value, and we don't need to change the sign. Remember, our math says we don't have to. So this is negative 0.403 volts. If you take a look, let's just see what our net ionic equation is for this, since we're actually determining that. Our electron transfer is balanced already. So there's no need to multiply either or both of those half reactions by a coefficient. These cancel just the way they are. So we have Sn plus 2Aq plus CD solid yields SN solid plus CD plus 2AQ. There is our overall net ionic equation that is set up by virtue of these two half reactions in this voltaic cell. So let's calculate E cell, which is E reduction cathode minus E reduction anode. So we have minus 0.136 minus negative 0.403. And when you do that, we do indeed get a positive answer of 0.267 volts, which means that even though both of these half reactions have a negative value for E, we can still, if those half reactions are placed at the proper electrode, get an operating voltaic cell. Doesn't produce a lot of voltage, so you're not going to get a lot of current out of that thing. But if you have devices that don't require much current, then this would work just fine. Okay? So when you're given two half reactions, such as we were here, and asked to determine how you would produce an operating voltaic cell using those two half reactions, you're going to look at the values of E, all right? Whichever one is more positive, that's the one you're putting at the cathode, all right? The other one will go at the anode. When you do the subtraction, you're going to get a positive value for E cell. Your cell will work, okay? All right, next. This is the last thing we're going to do today with this lesson. Scoot this up here. There we go. The table of standard reduction potentials can also be used to determine how strong of an oxidizing agent a substance is, or how strong of a reducing agent it is. All right? So here's what you got to remember. The larger the value of E, all right, the more positive, probably be a better way of saying that. The more positive or larger the value of E, all right, the more easily the substance is reduced. In other words, the more positive, and we've said this before, the more positive that value is, the more that substance wants to be reduced. Something that wants to be reduced is going to cause something else to be oxidized. And so we say then it is a strong oxidizing agent, all right? In other words, something that wants to be produced or wants to be reduced, all right, is going to cause something else to be oxidized. That's why we call it an oxidizing agent, okay? The smaller or more negative the E value is for a half reaction, the less easily that substance is reduced, which technically means the more easily it wants to be oxidized. All right? So here we're talking about metals, all right? So metals, don't want to be reduced. They want to be oxidized. So their values of E are mostly negative, all right? They vary, of course, but they're mostly negative. So if they want to be oxidized, then that means then something else is going to get reduced. And so we say that it makes a good reducing agent, right? And a not so good oxidizing agent, all right? So the more positive the value of E is for a particular half reaction, the more that substance wants to be reduced. That makes it a good oxidizing agent. The more negative the value of E is for a substance, for a half reaction, then the more that substance wants to be oxidized, which means it becomes a good reducing agent. All right. So let's look at the next example here. Scoot this up. There we go. There. For the following substances, use the table of standard reduction potentials to list their relative strengths as oxidizing agents. All right, oxidizing agents. So that means that they want to be reduced. All right, which means we're looking for a more positive value of E. All right, so as I look these up, so the nitrate ion, the half reaction that involves the nitrate ion, let's see, there it is right there. It's about halfway down the right-hand side. 0.96 volts. Just write that right there. The silver half reaction is actually the very first one. That is 0.799 volts. And the dichromate one, let's see, we did that earlier today. Here it is right here, about 3/4 of the way down the left side. That is 1.33 volts. So based on those values, which one of these three substances wants to get reduced the most? All right. Well, it's going to be the one with the greatest value or most positive value of E. All right. Which is the dichromate ion. All right. So this would make the strongest oxidizing agent because it wants to be reduced the most. All right. This is the smallest of the three values of E, or I should say the least positive of the three values of E. This would then be the weakest oxidation agent because it wants to be reduced the least of those three. And then this one would be in the middle. Okay. Now, what if the question instead have asked to rank their ability as a reducing agent? So let's look at that. All right. Well, something that's a good reducing agent wants to be oxidized, which means it's going to have the least positive value of E. That now becomes this one. So this was the weakest oxidizing agent, which then is going to make it the strongest reducing agent of these three, of course. This one, which was the highest value or the most positive value of E, which made it want to be reduced the most, which made it the best oxidizing agent, now is the opposite. This would be the weakest reducing agent, all right? Because here, as a reducing agent, something that wants to be oxidized, we're looking for something that's more negative, right? Of course, none of these are actually negative, but this is the least positive or most negative of the three. This one is still in the middle of those three anyway, all right? So we can use the value of E to say comparatively how good or not so good a substance could be as a reducing agent or an oxidizing agent based on the values of E. So that's going to end the first part of our lesson on additional voltaic cell calculations. We have an assignment related to this lesson. I believe it's called Voltaic Cell Calculations number 2, if I'm not mistaken. We wouldn't be able to finish that yet, but we could certainly get started on it. I think the original do now said that after today's lesson, you would be able to get through, I believe, up through number 11. But the second lesson over additional voltaic cell calculations is coming up next. And so once we get through that one, you should be able to then finish this assignment. So until next time, I'll catch you later. Everybody take care, stay safe, and I will see you again soon. See you later.